In this video, we're going to look at how we sequence proteins. And the idea behind sequencing proteins is a lot like how you sequence DNA. For proteins, though, you can have multiple chains. So the first idea is that you need to separate your multiple chains. You can use Edmond degradation to remove N-terminal residues one at a time, or you can use mass spec to identify amino acid sequence by mass to charge ratio. And then once you get your sequence, you can deposit it into an online database for other researchers to use. So why would you need to sequence a protein? Well, first off, if you have a mysterious protein and you don't know what the sequence is, you would want to know what you're working with. Some reasons for doing this is without the primary sequence of amino acids, you do not know what the 3D structure is. And without knowing the 3D structure, you don't really know how this protein works. By looking at your sequence, you can see how proteins have evolved over time. And a lot of diseases are caused by a change in amino acid composition. Therefore, if you sequence a protein of somebody who has a disease and you see a change in that protein, you can link that to the disease. So let's look at how you can analyze N-group residues, and this is Dansyl chloride method. And this is your N-terminus. And the idea is you add this reagent that's called Dansyl chloride, and you do this in the presence of acid and high temperatures. What will happen is that these two compounds will react. The chlorine will move off, and your Dansyl chloride will attach to your N-terminal residue to make a Dansyl peptide. And then, in the presence of water, this Dansyl peptide will be released. And it is fluorescent, and based on whatever amino acid is this R group, a different fluorescence signal will be shown. And so by doing this, you could continuously chop off N-terminal residues one at a time to see what amino acids are part of your peptide. Now, when you are doing sequence analysis for proteins, like I said, you do have to separate your peptide chains. Now, if they aren't connected by disulfides, then it's easy enough. You just use heat and they will come apart. However, if you have two cysteines on different polypeptide chains, they can form this disulfide bond. And so we need to reduce that or break this disulfide bond to separate the chains. And the common reagent to use that is 2-mercaptan ethanol. 2-mercaptan ethanol will reduce this disulfide bond, these sulfurs, then you will have a free disulfide bond. And then you can add another reagent, iodol acetate. This iodol acetate will bind to the actual cysteine molecule to make carboxymethylcysteine. And this carboxymethylcysteine can't reform a disulfide bond. So this helps to prevent reforming of any disulfide bonds. Now, in general, you can't sequence peptides that are longer than 25 residues. So much like sequencing DNA, when you sequence proteins, you need to break apart your peptide into smaller fragments. And the enzymes that do that we call endopeptidase. Endo for inside, peptidase for breaking peptide bonds. Now, there are also a class called exopeptidases that will cleave the N and C terminus. And here we have just a list of different endopeptidases, and they'll tell you, where or what amino acids that they will cleave. So here, for example, we have the peptide bond to be cleaved, residue number N and N-1. So if we read this table, N-1 is any positively charged residue, so Arg or lyse. And so it will cut, trypsin will cut after any Arg and lyse as long as the next residue isn't proline. And so you can use these endopeptidases to just cut up your your peptide in the smaller fragments. And there is another one not listed on here that's commonly used, CNBR. It will cleave on this carbon or carboxylic acid side of methionine. Now, let's take a look at sequencing peptides now. So another way we can sequence peptides is through using the reagent PITC. So PITC, again, will interact with the N-terminus. And you do this in the form of basic conditions. After you have this reaction, you add trifluoroacetic acid and hydrous. That means no water, it's pure trifluoric acetic acid. And what happens is that a reaction in which your PITC amino acid cyclizes and it breaks apart from your terminal residue. You can then look at this residue and determine, okay, what amino acid was connected to it, and for this your original peptide actually is still remaining active, and so you can go back and do another round and another round until your peptide is sequenced. And the great thing about this method is that you don't need a lot of protein to sequence it. It will do less than 0.1 micrograms, or you only need 100 nanograms of protein for this to happen. Now, after you sequence your small fragments, you have to put everything back together. And so it's a puzzle, just like for DNA. If you remember to sequence DNA, you have it in small fragments, and you reline up the fragments. Same idea with proteins. You have small fragments, and you just overline the fragments. And you also want to do a sequence in which you don't break the disulfide bonds, so you can see where your sulfide bonds actually happen. This will tell you some of the actual 3D orientation of your amino acids. If you know that these two cysteines are in a disulfide bond, you know that in fact they have to be close in space too. Now, commonly, most people don't use the methods I talk about anymore. They use what's called mass spectrometry. And mass spec is where you measure a charge to mass ratio. That's what M divided by C is. Mass, Z is charge. And the idea is you have your protein, you have it broken up. You put it into this capillary and you hit it with extremely high voltage, 4,000 volts. What happens is that you turn your peptides into charged droplets, almost like when you sneeze out little droplets. Same idea here, but with proteins. Then you have it go through this vacuum and you can evaporate this solvent and you're just left with charged proteins. These proteins are going through a high vacuum now, and they hit a detector. And with that detector, you get this mass to charge ratio along with their abundance. And by the peaks that you see, you can determine, okay, what amino acids, what polypeptides did I see based on their mass to charge ratio. And we'll look more at these numbers in class about what do they actually mean for us. But that is the end of this video, and I will see you in the next one.